Hi, my name is Andrew Pace, and my project is a filtered Rayleigh scattering analysis of three liquid fuels, ethanol, toluene, and dodecane. My project is sponsored by the National Science Foundation and the Combustion and Gas Dynamics Laboratory here at UConn. The goal of this project is to determine the filtered and unfiltered laser Rayleigh scattering versus temperature relationships for the selected liquid fuels. Laser Rayleigh scattering, or LRS, allows for temperature measurements of a flow or flame by exploiting the temperature dependency of Rayleigh-Brillouin scattering. The reason I need the filtered LRS signal is to pair LRS simultaneously with particle image velocimetry, or PIV. PIV uses a particle-seeded flow to determine a velocity field, but these particles create excessive Mie scatter that makes Rayleigh scattering measurements impossible. As shown in Figure 1, a molecular iodine filter can be used to filter out Mie scattering while letting a portion of the spectrally broadened Rayleigh scattering through. The top image in Figure 2 shows an image taken without the filter, and the white spots in the image are Mie scatter. The bottom image is taken with the filter, and you can see that the white spots are removed. This filter allows for PIV and filtered LRS thermometry to be performed simultaneously to create 2D temperature and velocity maps of a flow or flame. This would otherwise be impossible. The Combustion and Gas Dynamics Laboratory currently uses these techniques to study bluff body stabilized turbulent flames, which are the basis for a lot of propulsion technologies such as airplane engines. This project has three objectives. The first is to design a mass flow system that can vaporize and heat the selected liquid fuels to a range of relevant temperatures. The second is to use the mass flow system to collect the LRS data using the laser and cameras in the lab. And finally, I need to process this data to determine the LRS versus temperature relationships of the selected liquid fuels. The goal of my mass flow system is to vaporize fuel in a heated nitrogen flow. This can be broken up into three separate objectives: temperature control, vaporization of the liquid fuels, and mass flow control. The different arrows in the image on the slide show the flow path of nitrogen fuel to the outlet, with some parts missing due to design refinements and iterations. This simplified block diagram shows the flow path and important parts of the mass flow system. The nitrogen is supplied from a pressurized nitrogen bottle and is split into three flows. There's a nitrogen flow to the nebulizer, the heated main flow, and the heated co-flow. The temperature of the heated nitrogen flow is controlled by a PID controller connected to an inline heater. Heating tape connected to an Omega temperature controller and insulation prevent heat loss from the heated nitrogen flow to the surroundings. A Maynard nebulizer is used to break the fuel into small droplets. These fuel droplets have a small surface area to volume ratio that increases the rate of vaporization. The heating tape and insulation prevent condensation on the walls of the piping, and a heated co-flow of nitrogen prevents condensation at the outlet. The composition of the fuel-nitrogen mixture at the outlet is needed to calculate the LRS signal from the fuels. This can be calculated by controlling the flow rates of nitrogen and liquid fuel. A syringe pump not shown in the image will control the flow rate of the fuel. Pressure regulators and critical flow orifices control the flow rates of nitrogen. A co-flow of nitrogen prevents the condensation of the vaporized liquid fuels and the diffusion of atmospheric species into the mixture that could contaminate the LRS signal. An inline heater controlled with a PID controller will be used to heat the co-flow using the same technique as the main flow. This diagram shows what is meant by coaxial outlet and co-flow. Finally, an embedded thermocouple close to the outlet is used to estimate the fuel-nitrogen mixture temperature. The filtered and unfiltered LRS signals are determined using the experimental setup shown in the image. A camera situated behind an iodine cell records the filtered LRS signal, while a second camera records the unfiltered LRS signal. The laser is directed over the outlet by a series of mirrors before it is formed into a thin sheet using a plano-convex cylindrical lens. In addition, a back reflection off a mirror is used to calculate shot-to-shot wavelength and power measurements. These images show what the data collection system looks like in real life. A green line is used to show the path of the laser. To initially test my mass flow system, I calculated the temperature of a heated nitrogen flow using two different methodologies. I compared the temperature calculated using LRS thermometry to the temperature read by a thermocouple downstream of the outlet. If the temperatures matched, I knew that my mass flow system was working as designed. This is the procedure for processing the images from the initial test. They will be laid out in more detail on the following slides. The first step is to calculate a reference filtered LRS signal at each pixel. This is done by taking a set of instantaneous images of atmospheric air at room temperature. A low-pass filter is used to reduce the Mie scattering by eliminating any pixels above a certain value. A time average of the image set will remove any effect the reduced Mie scatter has on the data. The image is finally cropped to the laser sheet. The next step is to calculate the LRS signal from the heated nitrogen flow. This is done by taking a set of instantaneous images of the heated nitrogen flow. Image filtering techniques are used to filter out the Mie scatter from the instantaneous images. Finally, the instantaneous images are averaged together and cropped to the dimensions of the laser sheet. The ratio of these two signals is needed to calculate the temperature of the flow, using the LRS thermometry equation shown in the slide. The final step is to multiply the ratioed filtered LRS signal by known and calculated values to convert the raw LRS data into temperature at each pixel. This resulted in a mean temperature of 438 Kelvin for the heated nitrogen flow. The temperature read by the thermocouple was 458 Kelvin. However, this data was taken before a heated nitrogen coflow was implemented, so there was heat loss to the unheated coflow that could account for this difference. The next steps in this project are to implement the heated coflow design and adjust the image processing techniques to calculate the filtered LRS signal from the fuel, before characterizing the temperature relationship. I'll use this data to perform filtered LRS thermometry studies on bluff body stabilized flames for my master's thesis. Thank you for watching and have a great day.